All right, let's kick off this explainer. Today, we're diving into something that literally sounds like science fiction, but is honestly the fundamental bedrock of our future digital security. We're talking about lattice-based cryptography. We're going to look at how this truly awe-inspiring world of mathematical geometry is stepping up to protect our most sensitive data from the supercomputers of tomorrow.
So what exactly happens when those supercomputers, quantum computers, break today's locks? Look, this is not just some hypothetical scenario. For decades now, we've relied on a few very specific mathematical locks to secure pretty much everything on the internet. But quantum computers are looming on the horizon, and they threaten to pick those classical locks with ease. We desperately need a completely new mathematical foundation to protect our digital lives. And, well, we need to understand exactly how it works.
Okay, let's dive into this. Here is our roadmap for today. 1. The quantum security threat. 2. What is a lattice? 3. The hard lattice puzzles. 4. Real-life lattice encryption. And 5. Common quantum misconceptions.
Starting right off with Section 1, the quantum threat and the new need for security.
Back in August 2024, the government's NIST agency, that's the National Institute of Standards and Technology, officially drew a line in the sand. They highlighted a pretty stark contrast. Our traditional locks, things like RSA and elliptic curve cryptography, which secure everything right now, from your banking to your private messages, they're totally vulnerable to quantum attacks. Because of that, they're being replaced by the new quantum-safe standards. Specifically, we're talking about Kyber and dilithium. These are lattice-based solutions explicitly chosen to come to the rescue of the internet.
So, just to do a really quick recap, quantum computers are breaking our old locks. RSA and ECC are out. NIST's 2024 solution? The lattice. Kyber and dilithium are the new standards moving forward.
Moving on to Section 2. What exactly is a lattice? Let's demystify the math a bit here. The crucial point is, a lattice is really just a regular, repeating arrangement of points in real space. Seriously, just visualize an endless, perfectly spaced pegboard, or maybe a meticulously laid-out city grid. That right there is your lattice, and it sits at the absolute heart of these new security standards.
Now, imagine you have two different maps for navigating that pegboard. Any lattice is defined by its basis, which you can basically think of as your set of directions for jumping from point to point. A good basis map gives you short, straight, orthogonal directions. It's incredibly easy to navigate. But a bad basis map, it uses the exact same lattice of points, but the directions are just these long, skewed, overlapping lines. Navigating the grid with this tangled map makes finding your way extremely confusing.
All right, quick summary. Your lattice is your pegboard and your basis is your map. Good maps are short and straight, bad maps are long and tangled. Honestly, keep this map analogy in mind because it's the secret to literally everything that follows.
Section 3. The hard lattice puzzles and how we're actually building the fortress.
The first great physical challenge here is called the shortest vector problem, or SVP. The challenge is super simple to explain. Just find the closest physical peg to the center origin point. Now, on a flat grid, this looks totally trivial, right? But imagine doing this not on a flat grid, but in thousands of dimensions simultaneously. Without a good basis map to guide you, finding that absolute shortest path back to the center in a massive, multidimensional grid is a puzzle so incredibly complex, it would literally take a classical computer billions of years to solve.
And this brilliantly illustrates our next problem. Imagine trying to find the nearest black lattice peg to a random target, like the blue target dot you see here. This is our second major challenge, the closest vector problem, or CVP. If you've got a bad map, a skewed basis full of long, tangled vectors, figuring out which physical peg is actually the closest across thousands of dimensions becomes completely impossible.
So, to attempt to solve this, mathematicians use something called Babai's rounding method. It basically breaks down into 3 simple steps. First, you look at your map to estimate the target's location. Second, you guess the closest intersection. Third, you round or snap to the nearest whole peg. But here is the massive catch. The accuracy of your snap depends entirely on the quality of your map. With a good map, you round accurately. With a bad map, your rounding throws you wildly off course, and you completely miss the closest vector.
To wrap up these puzzles real quick, SVP is finding the point closest to the center, and CVP is finding the point closest to a random target. These are the ultimate geometric locks. They are virtually impossible to solve without a good basis map.
All right, Section 4, real encryption. How does this actually secure the internet?
Imagine a massive grid of random numbers. The short integer solution, or SIS problem, challenges you to find a tiny hidden pattern within that grid that perfectly cancels out to 0. Now here's what is absolutely mind-blowing. Finding this small non-zero solution in a mathematical matrix has been rigorously proven to be mathematically identical to solving one of those impossible multidimensional lattice geometry puzzles we just talked about.
This hidden pattern problem is actually the secret to modern digital fingerprints. We use it to create cryptographic hash functions. If a hacker wants to forge your data, say they want to find a collision of two files that look perfectly identical, they have to solve the SIS problem. This guarantees that breaking the digital fingerprint is just as mathematically hard as breaking the impossible lattice puzzle itself. There's no way around it.
So, abstract geometry literally translates into real-life security. Hiding a specific small pattern in a mathematical grid creates highly secure collision-resistant hash functions which act as our digital fingerprints. Breaking the fingerprint means solving the impossible lattice puzzle. This undeniable, unbreakable mathematical link is the precise foundation securing the new dilithium standard across the globe.
Let's move to our final section, Section 5, Common Quantum Myths. It's time to separate fact from fiction.
Look, it is a major myth that quantum computers are instant, magic decryption machines that are already out there picking our digital locks. The reality? Their exact timeline for development is highly uncertain. They are not breaking our encryption today, and honestly, we simply do not have a definitive date for when they actually will.
So to quickly recap the misconceptions, quantum computers are not magic, instant devices. The timeline for them breaking things like RSA and ECC is completely uncertain. However, and this is a big however, because the eventual threat is so severe, we are proactively building and standardizing these quantum-safe lattice locks today. It's a powerful, active present defense grounded in absolutely unyielding math.
Which leaves us with a final, completely fascinating thought to ponder. If the hypothetical, incredibly advanced supercomputers of tomorrow cannot solve these simple geometric pegboard puzzles, what other unbreakable mysteries are hiding in plain sight within the mathematics of nature? Thank you so much for joining me for this explainer, and keep exploring those mysteries.